Okay.
Are you not ready yet?
It's just all of a sudden started turning off.
What do you need help with?
Making it work.
Oh, the Wi-Fi. Okay.
Outside. What? Am I blue? Blue. Yeah. Okay. For those of you right in front of me, this is going to be a full intro because we're recording as well. So I'm going to speak to you and I'm going to speak to everyone who's online. So hello and welcome to this evening's Star Party. This is a very special Star Party because for the first time, we are offering something online as well as here on Observatory Hill at the very same time. So we haven't done that before. So forgive us any technical glitches and such that's been going on tonight. Today has also been, of course, it's International Astronomy Day. And we have been at the museum most of the day, meeting with so many of our members and our volunteers and the public for the first time in person in over 2 years. It's been wonderful. But before I get started, I want to take a moment to ground us. So we want to acknowledge and respect the Sankotan speaking peoples, the Wasanic, the Tsewat and Sartlet First Nations, on whose traditional territory this observatory stands, and on whose traditional territory we live, work, and play. We share with those peoples a historical relationship with the night sky. I, of course, encourage you to find out about the traditional lands that you are either joining us from or that you live on. So, hi. I am Amy, and I'll be one of your hosts this evening, of course. At the center, you'll also see Lori, and online, you'll also see Ben and Dawn. Tonight, Tonight we have Chris talking about the stories behind the two largest space telescopes, the Hubble and the James Webb. So, Christopher Gainor is a historian of technology, specializing in space exploration and aeronautics. He has written 4 books on the history of space exploration and 2 on Cold War history. His most recent book is a history of the Hubble Space Telescope operations, and it's been published by NASA. Chris is editor of Quest, the History of Spaceflight Quarterly. From 2018 to 2020, he was also president of the Royal Astronomical Society of Canada, and he is a fellow of the British Interplanetary Society. He holds a Ph.D. in the history of technology from the University of Alberta, and has worked as a history instructor at the University of Victoria and the Royal Military College of Canada. Chris will be talking about the stories of the two largest space telescopes, the Hubble Space Telescope, which was launched in 1990 and is still operating after 32 years, and the James Webb Space Telescope, which is about to begin operations in space after its launch December 25th. I really hope that you enjoy the presentations. Here's Chris.
Well, thank you. It's really a pleasure and an honor to be here tonight. This has really been an exciting day for all of us working on Astronomy Day here, because we actually haven't seen each other in person for a couple of years. I hadn't been up here for 2.5 years, which it just amazes me. So it's really exciting to be up here again, and seeing all our friends and making new friends. So in the last few years, it's been my pleasure to be working on this book here about the Hubble Space Telescope, and I got to spend some time down in the States meeting some of the people behind it. And while I was down there, I was also able to keep track of the construction of the James Webb Telescope. It was actually being put together at one of the space centers I was visiting, the Goddard one, as you see on my shirt here. So on this slide here is the cover of my book, and then you see a stamp for the Webb Space Telescope, and they just announced it about 2 or 3 days ago that this stamp is coming out. It's not even on sale yet in the US, but it will be shortly. But I'm just going to walk you through the stories of these telescopes, and I'm going to start off with of course, well, perhaps the most important question, which is why? Why do we need space telescopes when we have great big ones like the one across the parking lot here? Well, of course, in space, you don't have to worry about the atmosphere. You don't have to worry about clouds or precipitation or turbulence in the atmosphere. It's a little bit like when you go swimming and then you get underwater and look up, and everything is distorted. The atmosphere does that, but it also blocks out a lot of light from different wavelengths, which is a good thing for us, because if it didn't, we wouldn't be here. But it's not so good for astronomers, because they can get a lot of information from different wavelengths of light. So for these, in this slide here, we can see Hubble, which looks at visible wavelengths, which is what we can see when we look up with our eyes or with a telescope here. But it also looks into the ultraviolet portion of the light spectrum, and also the infrared portion of the light spectrum. And those are valuable for astronomers. Now, these telescopes don't only take photos, they also make observations with spectrographs, and sometimes it's done with prisms or similar devices, which breaks light down into its component parts. And that is like taking the fingerprint of stars. It tells you what they're made of, what elements they're made of. They tell you about their location, and even help you deduce where they are in the universe. So, and over time, a number of telescopes have been sent up to look at various wavelengths. There was now Hubble was not the first space telescope. They started launching them in the 1960s, but they were smaller telescopes, and they only they didn't get much public attention because they were just taking spectrograms of the stars, and they weren't really taking images that would get people's attention. But in the 1990s and the early part of the 21st century, we had what was called the Great Observatories from NASA. And the most famous one is the Hubble Space Telescope. And I showed you it was operating in visible light, a little bit of the near infrared and sort of a little bit of the ultraviolet. And then we have the Chandra telescope, which is actually still operating. It looks at X-rays. We get stars emit X-rays, and they tell us certain things about the what's going on in the stars. And then the Compton Gamma Ray Observatory, which was looking for gamma rays. It's not operating anymore. And then this one here, this is the original name, Certif, which it was named after Spitzer, the Spitzer Space Telescope, and it was looking in the infrared. And we'll talk a little bit about the infrared as we go forward. So now only 2 of these are operating, but these have given us a lot of information about the stars that you just can't get from the ground. So the Hubble Space Telescope is named after Edwin Hubble. And in this stamp, he's shown here with the Mount Wilson Observatory, which is near Los Angeles. And later on in his life, he worked at Mount Palomar when that opened in the last few years of his life. But later this year, we're going to be celebrating the 100th anniversary of his big discovery. 100 years ago, astronomers weren't sure about the dimensions of our universe. Many thought that what we call the Milky Way galaxy, that was the universe. And that some of the faint fuzzies we saw in the skies, like something that was called the Andromeda Nebula, was actually something in the Milky Way. Well, earlier, a few years earlier, astronomers had kind of figured out that they could determine the distance of stars from us by looking at a special type of star. And so 100 years ago, Hubble took an image of the Andromeda Nebula, what was called the Andromeda Nebula, and realized that one of the stars fit into this category. And he calculated the distance of that star from us at roughly 1 million light years. Now, he was actually out a little bit. The distance is actually 2.5 million light years, but it basically signified that the Andromeda Nebula was actually a galaxy of its own, and that our universe was much bigger than our own galaxy, that Andromeda was quite a distance from us. And Andromeda is certainly the most prominent galaxy outside of our own, with the exception of the Magellanic Clouds that you can see in the southern hemisphere. So this expanded the universe in our view. And one of the important things that Hubble was the Hubble telescope was going to do was to help determine the dimensions of our universe. So that was a very appropriate name for that telescope. So here's a schematic of Hubble. You can see Hubble is about as big as a school bus. It's quite big. And its main mirror is located over here. And it's about 94 inches across, 2.5 meters, which is bigger than that mirror you see there, which is, I think, 74 inches across, something like that, 72, 74 inches across, not even 2 meters, and that's the original mirror for the big telescope over there. So this is a fairly big mirror. So the light comes down here, bounces off this mirror to a little secondary here, and then down here is where there are different experiment packages, and there's the main cameras here, there are guidance sensors here, and then there are other experiments here, usually spectrographs. And Hubble was designed to operate with the space shuttle, which meant that these could be changed out by these instruments could be changed out by astronauts on the space shuttle. And that turned out to be a very fortunate thing for Hubble, given later events. Hubble doesn't use thrusters to move around. It has gyroscopes which tell it which way it's pointing. And then it has momentum wheels which turn and change its direction. It is only located about 500 kilometers above the Earth, about 350 miles roughly. And so often it's passing behind the Earth relative to what it's looking at. It's quite complicated to keep operating, but of course it's easy to reach because it's relatively close to Earth. And as I mentioned, it operates on solar power. So this is just a list of some of the instruments that have been on Hubble. Some of them are still there. But Hubble today is actually quite a different telescope from what it was when it was launched in 1990, because a lot of the instruments that are there today are a lot more up to date and a lot more powerful than the original instruments. So you can see most of the instruments are either cameras or spectrographs, and then there's a couple of specialized instruments at the bottom of the list. And these images here, this is one of the cameras for Hubble, and this is one of the spectrographs being changed out by an astronaut on one of the shuttle missions. So just very quickly, the Hubble and Webb are not only telescopes in space. You have a whole infrastructure on Earth and also elsewhere in space. This was especially important for Hubble, is that you have communication satellites. Hubble would, information from Earth would be beamed up to that satellite up there called a TDRS, Tracking Data Relay Satellite, and then back down to Hubble, and then the data from Hubble would go up to TDRS and then down to Earth. And once it was got to the receiving station, then it would go to the control center at the Goddard Space Flight Center. Now, you may not have heard of Goddard, but it's a very important place for NASA. It's just out in the suburbs of Washington, D.C. in Greenbelt, Maryland. It controls a lot of the scientific satellites like Hubble, and it's also a lot of the scientists at Goddard are quite heavily involved in things like using satellites to look at climate change on Earth. And so a lot of the data we get about climate change originates from Goddard. It's quite the place. About 50 or 60 miles away, half an hour's drive, an hour, depending on the traffic, is you go to Baltimore, and at the Johns Hopkins University, there's a Space Telescope Science Institute. And that's where you have scientists working who are dedicated to Hubble, and also where some of the scientific work on the data is done, some of the processing. Now, the people who get time on Hubble, and James Webb for that matter, come from all over the world. some of them work in that building, one of the buildings you drove by on the way up the hill here. There have been people at the DAO who've been involved in Hubble since day one, and use it for observations. There's also the data from Hubble is also stored at the Institute and also in Europe, because Europe is actually a partner in Hubble. And there's a third place on Earth where the data is stored, and you drove by it on the way up the hill here. It's at the Canadian Astronomy Data Center. Now, Canada isn't a formal partner in Hubble, but our government back then decided it would make sense for us to build our own data center. So we got a complete set of data, and so a lot of scientists today, they don't say, "Oh, I'm going to want to make this observation with Hubble." They'll go and see if it's in the data banks, and often it is, and they can dig it out. It's almost like an extra observatory. But anyway, this institute is very important. Now, with James Webb, it's a bit of a similar setup, but actually the control center for James Webb is here at SDSCI, because it's in some ways it's a little less complicated to control, so they set up the control center in there. So after many delays, Hubble was finally launched into space on April 24th, 1990 on the shuttle Discovery. And the next day it was deployed thanks to the Canadarm, as you can see in this image. And of course, the scientists were very excited, and a lot of the public too, to see what Hubble would come up with. Well, there was a very big shock. They discovered that the mirror on Hubble, that great big mirror, bigger than that one, was ground precisely to the wrong shape. And how that happened was some corners were cut on a testing device. And so the results from that device were erroneous, and nobody was really any the wiser to it until a few weeks after Hubble was launched, and they realized that all the images and other data were coming up to be blurry. So this was really embarrassing. You know, if you ever, one of the Naked Gun movies has a thing making fun of Hubble, and the cartoonists had a field day. The talk show hosts back then had a field day with Hubble. It was kind of a byword for failure. But the folks at the Institute and at NASA rolled up their sleeves after they got over their shock. You know, because this is, as you can see from this thing, $1.5 billion, which is a lot of money now, but it was even more money then. They figured out, well, how can we fix this? So one of the reasons they were able to fix it was because, of course, the shuttle was going to be coming up to Hubble anyway to change out instruments. And they figured they were able to figure out the exact nature and measure exactly the defect on the mirror. And then they built new, they were building new instruments anyway, so they changed them and fitted each instrument in effect with corrective lenses, like contact lenses inside, and put them in. And they started to install them on the next servicing mission, which took place in December of 1993. So this image was released shortly after that image, and then of course Hubble became a byword for success, and people forgot that it had this terrible problem because they had done such a good job of fixing it. But it's quite an amazing story how they did it, how they figured out how to deal with it. and the hard work that the astronauts put in to make those changes on that mission. Now, during the lifetime of Hubble, we have had 5 servicing missions to Hubble. And each one of those missions has been different from the others. Some had to actually happen with great urgency because parts of Hubble would wear out, like the gyroscopes especially. And others were dedicated to changing out instruments. But there were also things like repairs were done on Hubble which weren't contemplated when it was first launched. Hubble was supposed to last for 15 years. That's what they wanted originally. We're now up to 32 years. Now, the interesting thing is that the shuttle program came to an end 11 years ago. So the last mission to Hubble went up 13 years ago. And they did such a great job on the fixes that Hubble is still going 13 years after the last human hands touched it, which is really amazing because 13 years after any of the previous missions, it would be dead by now. But some of the instruments, like the gyroscopes, which are kind of prone to failure, the new ones are better. So Hubble is actually still going strong today, even though there's no way to replace it other than kind of like software or just staying one step ahead of it on the ground. Occasionally it has problems and it does go down as they deal with problems, but it's still going well. And they want to operate Hubble for at least 2 years in joint operations with James Webb, and I think they'll get that and some more. And Hubble is supposed to, in the 2030s sometime, it should be falling back to Earth, but it's a little early to say exactly how that's going to happen because they may send something up to make sure it's either knocked into a higher orbit or that it's brought back under direction, because some of it would survive the fall, and of course we don't want it to land on anybody's head. The chances are, even if it was uncontrolled, it wouldn't hit anybody because most of the Earth's surface is water. So, and by the way, it won't land on us up here in Canada because Hubble's orbit doesn't come this far north. So anyway, we'll see what happens, but I hope it operates for a few more years. Now, I'll just speak briefly about what Hubble has done. This is actually kind of a version of its most famous photograph, the Pillars of Creation photo, which was taken of M16, the Eagle Nebula. And it's called the Pillars of Creation because these are stellar nurseries. Those are stars being born up there. But there is sort of cosmic wind blowing against these, which creates these pillars. You're probably wondering, well, what's this here? Well, this is actually the same image, except this is in infrared. This is in close to visible light, and astronomers, even here, can see can see something like this, although of course the Hubble image is far clearer and far better. But this is in infrared light, and this gives you a bit of a taste of why astronomers are interested in infrared telescopes, because all this gas here is covering up stars and things you can see here. It's just kind of a different image. Different kinds of light has different qualities. So very quickly, what is Hubble discovered in those 32 years? And these are very this just scratches the surface. You know, I have a whole chapter in my book about Hubble and science, and even that just scratches the surface. But it's told us about what the nature of the universe and how big it is and how old it is. You know, roughly 13.8 billion years old, and that also gives you an idea of you know, that's how long it's been since the Big Bang. It also gives you an idea of how big it is. But before Hubble, a lot of people thought, a lot of the experts thought, well, the universe is expanding, but the rate of expansion is slowing down. And to their shock, they found out that it is expanding, but the rate of expansion is actually speeding up. And you might think, well, this might not be easily accepted, but the evidence was so compelling that it has been widely accepted. But this brings up questions like, how could this be happening? Because you have to have a certain amount of matter or energy to be driving it. And so this is why you hear people talking about things like dark energy, which is kind of a fancy way of saying we don't understand what this is. But for the time being, that's how we're going to explain this. And this discovery, by the way, doesn't involve only Hubble. It involves a lot of astronomers and other scientists working on with other space telescopes and other telescopes on Earth, including telescopes like the Canada, France, Hawaii telescope in Hawaii. And Hubble played an important part on that in that discovery, but not the only part. Another important thing was Hubble finding that pretty well every galaxy has what we call a supermassive black hole at its center, which is kind of holds the galaxy together in terms of the gravity. Now we have black holes around, and then you have supermassive black holes, which are thousands of times bigger. But that was an important finding. Another important thing that's been going on in the last 30 some odd years is exoplanets, planets orbiting other stars. You know, when Hubble was launched, there were no known exoplanets anywhere. We hadn't seen any. Now that the launch of Hubble actually had nothing to do with that, because it was earthbound telescopes where they first started discovering exoplanets, and that took place in the mid-90s. And one of the reasons for that is that Hubble is not a survey telescope. It's not something you use to just look around for stuff. You want to have a specific target. But once the telescopes on Earth, and actually some Canadian astronomers were quite involved in the work that led to the discovery of the first exoplanets. Once they started figuring out where they were, they launched dedicated telescopes such as the Hubble Space Telescope, and also one called TESS, which are looking for more exoplanets. And now they found several thousand. But and that's just kind of starting the search. But once they knew where some of them were, they started pointing Hubble and other space telescopes at these planets and their stars, and figuring out, well, what's going on in their atmosphere and what are they made out of. Now, of course, the big thing they're looking for is something like Earth. They haven't found anything exactly like Earth yet, but they are finding some fascinating things. I think some of the discoveries have just really exceeded our imaginations, and but some of them are close to speculation. There's a planet, and I forget what it's called. NASA's produced this travel poster to visit this planet, but the outstanding feature of it is that it's very much like Tatooine in Star Wars, because it has two suns. So it shows a couple of people standing on this planet and two suns going up. Another thing is that Hubble has been looking around our own solar system and has been involved in making some discoveries there. It helped point the New Horizons spacecraft at Pluto a few years ago, but it's also seen the comet crashes on Jupiter. There was one in 1994, which is very famous, and also followed storms on Saturn. It's kind of an observatory for what's going on in our solar system. So that very quickly is what some of the things that Hubble has discovered. But I would argue that this photo here, which came out in 1995, is Hubble's biggest gift to science. This is called the Hubble Deep Field. And the person who ran the Telescope Institute back then was persuaded to give some time on Hubble to just point at a very empty area of the sky. And this is an area close to the Big Dipper. There's not anything up there, at least when you look at it, even with regular telescopes here. You just said, what if we had a really long exposure? And I don't mean a 30th of a second or 10 minutes. I mean like a week-long exposure. What are we going to find? It's like a cosmic drill hole. And so they just pointed at it, and there was controversy, people saying, you're wasting your time, you're not going to find anything. Well, this is what they found. There's a lot of things in that empty area, and virtually all of these objects you're looking at are individual galaxies. There's a couple of stars in the Milky Way, but most of these are galaxies and looking very far away from us and looking earlier into the history of the universe. This was a jaw-dropping event. Incidentally, it was a huge event in the internet because when it was released, a lot of people were just getting their first computers with graphic interfaces. I remember I just bought my first Macintosh, and that was the first Hubble photo I downloaded into my computer. And I have a lot of company. So Hubble since then, in tandem with other space telescopes, such as the ones I was showing you earlier, have been taking images looking at different parts of empty real estate or supposedly empty real estate and looking farther back. And you probably see, well, you see these loops in here. And what the heck are these loops? Well, you know, Einstein discovered that gravity can bend light. And so these loops are actually galaxies behind some of these other objects here, and which have bent the light. And so this allows you to look even further back into time. And so this, what you see here, is one of our glimpses in one of our greatest looks into the distance. So this chart here is quite important. So this shows you, for example, you know, with a telescope outside there, this is about how far back you can look, you know, a few billion years. And then the original deep field takes you this far back. And then the more recent deep fields take us quite close to the early years of the universe. But to look beyond that, you need JWST. So that's why we have JWST. It's not the replacement for Hubble. We say it's the successor to Hubble because it is different from Hubble in a lot of ways. It is looking in the infrared because you might recall I said the universe is expanding. So everything is moving away from us. And that means that they shift into the infrared. So to see things And the farther you get away from us, the faster you're moving away. So you want to look into the infrared. So that's why they decided to build the James Webb Space Telescope as Hubble's successor and have it work in the infrared. And so why does it look so different? Well, it's quite different. It's in a different location. It's 1,000,000 miles literally from Earth. That's 4 times as far as the moon, the 1.6 million kilometers. And it has this great big sun shield here, which cools down the instruments and the mirror so that they are as cold as possible. Of course, when you get down, we all know centigrade and Fahrenheit, but you get down to the Kelvin, which takes you down to absolute zero. And some of these instruments are barely above 0 Kelvin, because that's what you need for an infrared telescope, because any heat is something that shows up on infrared instruments. So if you want to see what's really going on, you have to get things cooled down. So as you'll see in a minute, Webb is away from the sun, and it's always shielded by this sun shield, which is about as big as a tennis court. And so this is James Webb, the mirror being assembled a few years ago at the Goddard Space Flight Center, and you can see some of the people here working on it. And they have a viewing room, and you can see a fellow looking at it. That's me. So that gives you an idea of how big it is. And it's coated with gold because that's a little better for infrared observations. Now the mirror had to be folded up to go in the rocket. They couldn't launch it on the shuttle because, of course, the shuttle's out of business now, and it had to be all folded up, and everything had to unfold once it was launched. The work on James Webb really started in earnest about 20 years ago, and it had many delays along the way, and the expenses went up. It cost about $10 billion to build, but this had a great support from astronomers because it looks back in time further than anything else. So who is James Webb? This is James Webb here. Now, he is actually not an astronomer or scientist, but he was the guy who ran NASA in the 60s when they went to the moon. You know, getting to the moon was the signature achievement. So they decided to name it after him. So this is him back in the 60s with an early version of the lunar module. So after all these delays, James Webb was launched on Christmas Day. I got up early on Christmas Day 6 months ago, whenever it was, and watched this launch. Now, the Europeans are partners in this telescope, and one of their contributions was to launch it from their launch site on this Ariane rocket, which is very powerful. And you can see here that it was all folded up, and then in the first month it had to unfold. And I'll tell you, when I first saw the animation of this a few years ago, I thought, you've got to be kidding. And that's what everybody thought. But they pulled it off. It took about a month to get everything all unfolded, the sun shield out and the mirror unfolded. And then the end of January, they had a little celebration in their control center at the Space Telescope Science Institute. So that was the end of January. And so here we are, it's May, and we still don't really have the images yet because they're still in the process of getting things set up. There's a lot of fine work. And just before we get to that, this will give you an idea of where it is. So that's the moon going around the Earth. There's the sun back there. And this is a point called L2. It's a Lagrangian point. And that's a point where the gravity between the sun and the Earth are kind of in balance with each other. And actually, there's a number of spacecraft out there. Now, Webb is not sitting at this point. It's actually orbiting around it. And this orbit is actually bigger than the orbit of the moon around the Earth. But it goes around this way, and the telescope, as I point out, because the sun shield is never exposed to the sun, and so that's where it'll be. It's expected to operate for at least 10 years or so. And as I mentioned, there's no spacecraft that can go and rescue it if it conks out, at least that we know of. I've heard of a couple of people who are thinking about, oh, what could we do? But so far, things have gone very well, and they haven't had a problem. So, so there are these 18 mirror segments that I showed you in the earlier pictures, and they first of all had to be unfolded, and then they had to be precisely aimed, and I mean really precisely. And this little picture was taken by a camera on the telescope when they were all pointing in the right direction, so that they act like a single mirror. There were some earlier pictures where some were black and some were white, so they've got that far. And then about a month ago, they released this picture. Now this is of a star near the Big Dipper. I seem to be mentioning the Big Dipper a lot, but anyway, and this is brighter than what they'd usually be looking at. But what got people reacting was that you could see distant galaxies here. And this was just like a test picture, as an engineering picture. They weren't looking for anything in particular other than this star. And this impressed a lot of people. And so we have these instruments on board the James Webb Telescope, and they've got them pretty well set up and focused, but now there's kind of the fine work going on right now to commission them. But they released this image just a few days ago, a week or two ago, showing the various instruments. So I'm going to draw your attention to a couple of them. The fine guidance sensor, made in Canada, and this one here, nearest, made in Canada. You and I help pay for those instruments. And they are working fine, but there's still kind of some fine work that has to be done before we'll start getting the first images and the first scientific data from Webb. So those pictures are expected to be released in June sometime. I'm not sure of the exact date, but just to give you a little bit of sense, somebody did this. I'm not sure who on the internet, but this shows how much better they are than what we had before, because infrared telescopes have never been really noted for the image quality. But there was this telescope that was up about a dozen years ago called WISE, and it took this image of this area. This is in the one of the Magellanic Clouds, and then the most powerful infrared telescope up to now is Spitzer, which I mentioned before. That's a little clearer, but then look at this from JWST. So I think we're going to be in just a few weeks. We are going to be into some treats in terms of the images that are coming out and the data that will be coming down. So I've mentioned JWST working on things like looking at the edge of the universe, the early days of the universe, getting close to the Big Bang. It will be used for other things. I know that a big mission for the nearest instrument that Canadian folks have developed, will be giving us close-up looks at exoplanets. So we're going to find out more about those planets, and who knows, maybe we'll find somebody waving back at us and wondering if there's intelligent life here. I know I wonder about that. But anyway, this is the final slide, but this is a bit of a comparison. Here's the Webb mirror compared to the Hubble mirror. It's about 6 times the collecting area and some of the other things. So that's my talk. I don't know if we have time for questions, but I think we have a time for a couple of questions. So do you have any questions? Yes. Well, it doesn't have any thrusters or anything. Webb actually has thrusters to help keep it pointed. But Hubble, when the shuttles would come up to visit Hubble and they would berth Hubble in the back of it, then they would fire their jets and raise up the orbit a little bit. So it's coming down. And like I said, if sometime in the 2030s, they believe, depending on the amount of solar activity, it will come down if nothing is done. But it just uses those reaction wheels to kind of point itself, but there's nothing to sort of keep it up. It's getting closer and closer as time goes on. Any more questions? Yes. It still is, absolutely. I know there's some talk about it. I'm not sure when that's going to happen. There is some work going on a telescope called the Nancy Roman Space Telescope, named after a famous woman astronomer called Nancy Roman, and that's supposed to go up later in the decade. But I think that also kind of works a lot in the infrared. It's more of a survey telescope. It can look over wide swaths of the sky, whereas Hubble and Webb are just trying to look far away, but they have small areas in which they can look at. Just one comment about the looking in invisible light. The capacity of telescopes on Earth to look at them is improving. So and because of the increase in computing power, telescopes on Earth are able to overcome some of the problems from the atmosphere when they're looking in visible light. And actually some of the work on that has been done here. So you know, we had some earlier in the day, we were displaying some pictures that some of my pals from the Astronomy Club here in the RESC Victoria were taking. And people are saying, oh, that looks like a Hubble picture. Well, actually, it was just, you know, my friend Joe or my friend Bob. I'm not really a good astrophotographer myself, but we're actually doing some amazing things on Earth. So that will kind of compensate for the loss of the visible light thing from Hubble. Okay. I think I'll end it off here, and I hope you found this interesting. Thank you.
Hi, everybody. Hope you can see me here. And I'm going to share my screen.
Hey, Don.
Oh, really?
Okay,
Yeah.
so we've got some competing audio in the background, just so
Yeah.
everybody knows this is all a big
Okay.
experiment. We'll give it a try. And So I guess this is going out on YouTube. So if everybody leaves, maybe somebody someday will look at this portion. But in any case, I just wanted to tell you a little bit about what's up in the sky, because there's some very cool things happening right at the moment. And what we have over here is actually a view of the early morning sky. Hopefully you can see that. Ben, could you just nod if you can see that featured on the screen? Okay, thank you. And what we have here is a view towards the east and southeast, early in the morning, as I say, before 5 o'clock. And you can see all the planets or many of the bright planets are strung out in a line here. And this is, of course, close to the what we call the ecliptic, which is the plane of the Earth's orbit. And this makes complete sense because all the planets in the solar system were born out of this big, same spinning disk of gas and dust. And they still follow more or less the same plane as they orbit around the sun. And so don't miss this, but also notice that they are quite close to the horizon. Saturn is only about, if you put your fist up at arm's length, that's about 10 degrees. And so that's about how high that is off of the horizon. So you'll need a very clear horizon, maybe looking out over the water or something like that towards the east. So go to a beach or Mount Tolman or something like that. And I'm just going to jump now back to the evening sky. And in fact, I'll just do it this way. I'll try to do this quickly. So we're into twilight now, and I'm just going to bump it just a little bit later here. And I'm also going to get rid of that, that pesky line here, ecliptic. And look, we're now looking at the evening sky as we see it tonight. And I just want to, you might notice that the moon is the first quarter moon is over there. And this is actually a great phase for looking at it with a telescope or even binoculars to try to see some craters and so on. But the big thing this month is that there's going to be a lunar eclipse on May 15th, 16th, so Sunday night, May 15th. And the moon will rise during total eclipse just before the maximum phase, so just before 9 o'clock, if you have a clear view of the eastern horizon. And it'll be totally eclipsed, but it will still offer some very interesting views. So you'll actually be able to see it come out of the total phase during twilight. So pieces of it will likely be missing. It might even be hard to find the moon in the twilight, as a matter of fact. And there's so get your binoculars and telescopes and zoom lenses ready for that. And there's something interesting to think about as you're gazing at the moon over many minutes that night. And as we look up at the sky, we notice that things are, we know that things are various ages. And for the moon, notice that there are lighter and darker areas, and those more or less correspond to different ages in the history of the moon. The darker areas called Maria or Cs are sites of great impacts, and these are generally younger than the brighter areas. And so the Maria are around 3.5 billion years old. The lighter areas are about 3.9 billion years old. So you can even see some differences in time in that sense. And if you come up to the center of the universe, which you can now do again, of course, on Saturday nights, the nights that we're open, you can touch a meteorite that has been dated at 4.5 billion years old as our solar system. And this was part of the same meteorite fall that scattered a bunch of chunks across the desert in Arizona. And another chunk of that same asteroid that fell there was the first meteorite that provided an accurate age for the solar system at 4.5 billion years old. So that was worked out at Caltech in the 1950s. But if you touch it, just remember to wash your hands afterwards. So the star Arcturus, which is visible in the nighttime sky, is actually at about 7 billion years old. So it's worth thinking about that many, but not all of the things that we see in the sky existed before our solar system did. And our solar system was born out of the Milky Way. And if you're wondering where the Milky Way is, we can maybe scoot across to the northwest horizon, and I'll see if I can actually just get rid of some of the skylight that's interfering. And if there wasn't a sky glow down near the horizon, you'd be able to see it much better. And so the Milky Way is not overhead at this time of the year. It's sort of skirting the northern horizon. In fact, there's the summer constellation Cygnus. But as we move around towards the east and towards the south, you see that it's dipped down below the horizon in that part of the sky. So really at this time of the year, we're not looking at the Milky Way, we're looking up out of the Milky Way, and when we look right overhead, we're actually looking sort of out of the north pole of the galaxy where there's not as much gas and dust, but you can see a lot of galaxies, and see if I can bring some of those up here. And so they're the little red ellipses that we see here. These little yellow things are actually globular star clusters, and you don't see actually very many of what we call open star clusters. Those are actually over in the Milky Way. So you tend to find sort of a differentiation between the types of objects that you see in different parts of the sky. And these are objects in the Milky Way. But again, the galaxies are more distant, as Chris was saying. And this is a great time to look up into the nighttime sky to see them with binoculars or small telescopes, which you can with many of these galaxies that are overhead right now in the Virgo cluster. And of course, if it stays clear tonight, they'll be making images of these with Plaskett telescope in the dome. So that's great that we're finally back to that after 2 years. So I'd just like to thank, if there's anybody left listening, I'd just like to thank you for attending tonight virtually, and and hopefully as COVID goes away, we'll eventually, whenever that is, we'll be able to see you up at the observatory again. And so thanks very much for participating tonight. Hope you enjoyed it. Let us know how it went too. If you have any questions, please feel free to stick them in the chat. I don't know if there's any questions at this point. Any questions?
We've got 9 people watching in both YouTube and
That's great.
And Zoom.
Okay. Well, thank you, everybody. Nice to see Jim Hesser is here, and I'm sure Betty's there as well. So hello to you, and hopefully talk to the rest of you soon. So thanks, everybody, and I'll leave it to Calvin to shut us off here tonight. That's it for our programming, and we're expecting to have more expanded virtual programming, including things from the dome as the summer goes on. We're just figuring this out right now. Any questions in the chat, maybe, or on YouTube? No. Okay.